In this video, we're going to get some practice with related rates problems. In each case, we're going to want to identify a relationship between the variables or an equation. We're going to identify the known rate. And finally, the unknown rate. With number 1, we have a cylindrical storage tank has a fixed radius of 4 meters. Water is being pumped into the tank at a rate of 20 pi cubic meters per minute. How fast is the height of the water level rising? So right here, our 20 cubic feet per minute, that is a known rate. And we want to make sure we're using correct notation here. So we're talking about the rate of change in the volume with respect to time is equal to 20 pi cubic meters per minute. Next, for our unknown rate, they want us to find how fast the height of the water level is rising. So that's going to be a rate of change in the height with respect to time. So we want an equation that's going to give us a relationship between the volume of a cylinder and its height. The volume of a cylinder is pi r squared h. In this particular problem, the radius is given to us as 4 meters. So this volume formula becomes V equals 4 squared, which is 16 pi times h. Now we're going to take this equation and take a derivative with respect to time using implicit differentiation. So we have dv dt equals 16 pi dh dt. Now we plug in our known rate and isolate dh dt. Since the given volume has cubic meters per minute as the units, the rate of change in the height with respect to time will be meters per minute. Pause the video, do number 2. Number 3, the side length of a square is increasing at a rate of 5 centimeters per second. At the moment, the side length is 8 centimeters. How fast is the area of the square increasing? So once again, we're going to start with our equation, our known rate, and our unknown rate. If we label the lengths of each side of our square as x, then the known rate of 5 centimeters per second will be a rate of change in the side length x with respect to time, and that equals 5 centimeters per second. The question is ultimately asking for how fast the area of the square is increasing. That will be the unknown rate, dA dt. And they want us to find this rate when x is 8 centimeters. So we have a representing the area of the square and x representing the side length of the square. So our equation will be a equals x squared. Again, we're going to take a derivative with respect to time and use implicit differentiation. So we have dA dt equals 2x dx dt, and then we'll plug in the values that are given to us. So dA dt is equal to 2 times 8, dx dt is 5, and that will give us 80. And this is a rate of change in area, so that's centimeters squared per second. Pause the video, do number 4. Number 5, air is being pumped into a spherical balloon at a rate of 100 cubic centimeters per second. How fast is the surface area of the balloon increasing when the diameter is 50 centimeters? So again, we're going to find our equation, our known rate, and our unknown rate. The given rate is 100 cubic centimeters per second. That's the rate at which the air is being pumped into the spherical balloon. So that's going to be a rate of change in volume with respect to time. The unknown rate is the rate at which the surface area of the balloon is increasing. So that's going to be ds dt, where s is the surface area, when the diameter is 50 centimeters, which means the radius will be 25 centimeters. Now you'll notice here that we're dealing with both volume and surface area of a sphere. The equation for the volume of a sphere is V equals 4/3 pi r cubed. So here we have an equation that's giving us a relationship between the volume of the sphere and its radius. But you'll notice there's nothing on surface area here. The equation for the surface area of a sphere is S equals 4 pi r squared. Now the problem here is we're trying to answer a question involving surface area, but they've given us information about the rate of change in the volume. So let's start with our equation for volume and see what happens when we take a derivative with respect to t on both sides. So we have dv dt equals 4, when we multiply the 3 in front, pi r squared dr dt, implicit differentiation. And we have a known rate of 100 for dv dt, and we know that we are going to plug in 25 for the radius, and then we can solve for dr dt. And we get 1 over 25 pi. But notice, we don't want dr dt, we're trying to find ds dt. So now, let's go ahead and take a look at what happens when we take the derivative with respect to time of our surface area equation. So now we have ds dt equals 8 pi r dr dt. And we want to know the rate of change in the surface area when the radius is 25, and we have that dr dt is 1 over 25 pi at that time. And now we can simplify. And because we're dealing with surface area, we have centimeters squared per second. Pause the video, do number 6. Number 7, a 25-foot ladder is leaning against a vertical wall. The base of the ladder is pulled away from the wall at a rate of 3 feet per second. How fast is the top of the ladder sliding down the wall when the base is 7 feet away from the wall? So if this is our wall, the ground at a right angle, we have a 25-foot ladder like this. And as this ladder slides down, we have this quantity y getting smaller and this quantity x getting bigger. So again, we're going to want an equation, a known rate, and an unknown rate. In the question, we're being told that the base of the ladder is pulled away from the wall at a rate of 3 feet per second. So our value x is going in this direction at 3 feet per second. So that means that we have a dx dt, the rate of change in x with respect to time, is 3 feet per second. And the question wants us to find how fast the top of the ladder is sliding down the wall. So that means we're going down this way. So we're looking for a rate of change in y with respect to time when the base of the ladder is 7 feet from the wall. So that's when x equals 7. So looking at our triangle here, we've got an x, a y, and a 25, and they're related using the Pythagorean theorem. So there's our equation. And so we'll take the Pythagorean theorem and we'll differentiate with respect to t. We can multiply everything by a half. Now, we have a value to plug in for x, right? The 7 feet right there. We've got dx dt at 3 feet per second. We're looking for dy dt, but we don't have y. We want to know what y is when x is 7. In other words, we want a y value here. So looking at our triangle, we notice that when x is 7, we can find y using the Pythagorean theorem. That should give us y being 24. So now we can plug in 7 for x, 3 for dx dt, 24 for y, and we're going to solve for dy dt. Y is measured in feet, and since dx dt is equal to 3 feet per second, dy dt will be this negative 7/8 feet per second. Pause the video and do number 8. Number 9, a spotlight on the ground shines on a vertical wall 12 meters away. A woman 2 meters tall walks from the spotlight toward the wall at a speed of 1.6 meters per second. How fast is the length of her shadow on the wall decreasing when she is 3 meters from the spotlight? So first we'll go ahead and sketch this. Here we have our vertical wall. The spotlight is at this point here. And here we have our person 2 meters tall. In the question, we see that the spotlight is 12 meters away from the wall. So this distance all the way across here is 12 meters. And also in the question, we see that the woman is walking from the spotlight toward the wall at a speed of 1.6 meters per second. So we're going to make this distance here x, and we'll make the height of the shadow y. So the known rate is the rate at which x is changing, so that'll be a dx dt equaling 1.6 meters per second. The unknown rate is how fast the length of the shadow is decreasing, so that's going to be dy dt. And they want us to determine this rate of decrease when x is 3 meters, when the woman is 3 meters away from the spotlight. Now, the equation here is maybe a little trickier than the others that we've seen so far. What we need to notice is that there's a relationship between the two right triangles that we're looking at here. Namely, we have this green right triangle here, and we have this purple right triangle out here. Now, these are similar right triangles, which means that the corresponding sides are proportional. In other words, if we look at the small green triangle, we can say that x over 2, right, this horizontal length here over the height of the woman has to equal 12, the horizontal length of the purple triangle, over y. So again, we're just saying that the corresponding sides of these similar triangles are proportional, which means that if we take the ratio of the horizontal length of the green over the vertical length of the green, that should equal the horizontal length of the purple over the vertical length of the purple. Now, if we go ahead and isolate one of our variables here, maybe we multiply over the y, and then multiply both sides by 2 over x, we'll get 24 over x, which is the same as 24x to the negative 1 power. So that's going to be our equation here. So we'll go ahead and differentiate this implicitly with respect to t. Now we plug in the given values, so we plug in the 3 in for x, and dx dt is 1.6. This simplifies to negative 12.8 over 3, which approximates to negative 4.267 meters per second. So to get you started on number 10, notice that you have a 15-foot lamppost, and it's shining light so that this 6-foot tall person is leaving a shadow like this. And we have this distance here, we'll call that x. We can call this distance y. And we want to find the rate at which the tip of his shadow is moving. And that will require us to look at this full distance here, maybe call it capital D. So capital D is equal to x plus y. So now go ahead and find the rate of change in capital D with respect to time. Number 11, car A leaves an intersection heading north at 40 miles per hour. At the same time, car B is 6 miles east of the intersection and traveling west toward the intersection at 30 miles per hour. How fast is the distance between the two cars changing 6 minutes later? So let's start with the picture. If this is our intersection, car A is going north, let's say to here, and car B is traveling west towards the intersection like this. And this will be the distance between the two cars. So we could label this x, y, and z, and the relationship between these three lengths will be the Pythagorean theorem. Now we're given two known rates. We're told that car A leaves an intersection heading north at 40 miles per hour. So that's a change in y with respect to time. So dy dt is equal to 40 miles per hour. We're also told that car B is traveling toward the intersection at 30 miles per hour. Since car A is moving away from the intersection and car B is moving toward the intersection, we'll go ahead and make the rate of change in B's distance from the intersection negative. Now the unknown rate is going to be the rate of change in the distance between the cars, dz dt, with respect to time. And they want this 6 minutes later. Well, 6 minutes is 1/10 of an hour. So we'll take this information and we'll notice that car B was originally 6 miles east of the intersection. So the length of x is going to be 6 minus 30 miles per hour times 1/10 of an hour. Okay, again, the car started 6 miles from the intersection and then travels toward the intersection. So it's going 30 miles an hour for 1/10 of an hour. Well, that should equal 3 miles. Also, we need a y value 6 minutes later. Well, 6 minutes after A leaves the intersection, it's simply gone 40 miles an hour for 1/10 of an hour, right? This is a rate times a time, leaving us with a distance. We could then use the Pythagorean theorem to see that z has to be 5 miles. So now we'll take our Pythagorean theorem and differentiate with respect to t. Dividing everything by 2. Now we'll plug in everything that we were given and figured out above. So we found that x is 3 miles, dx dt is negative 30, y is 4 miles, dy dt is 40, and z is 5 miles, and we're finding dz dt. So that's negative 90 plus 160 equals 5 dz dt. That will give us dz dt equals 70 over 5, which is 14 miles per hour. Pause the video, do number 12. Number 13, a police car parked 50 feet from a large warehouse wall is rotating its light at 10 revolutions per minute. How fast is the beam of light moving along the wall when the beam strikes the wall at a point 50 feet from the point on the wall closest to the car? So this one you might want to read more than once, but the basic idea is that we have 50 feet between the police car at this point. We'll say that's the police car's light. 50 feet from this wall. And this light rotates, say, in this direction, and we'll call this the angle theta. This here is the wall. Let's go ahead and label the distance that the light has traveled after completing the angle theta. We'll call that x. And then we'll call the distance here r to represent radius. Imagine this light is going around in a circle. That would be the radius of the circle. Now, we're going to need an equation, a known rate, and an unknown rate. So the known rate here is 10 revolutions per minute. Now we know every full revolution is 2 pi radians, so that's 10 times 2 pi, which gives us 20 pi radians per minute. The question is asking how fast is the beam of light moving along the wall when the beam strikes the wall at a point 50 feet from the point on the wall closest to the car. So we're talking about how fast is this distance changing. In other words, we want to find dx dt when x is 50 feet. What does that tell us about theta when x is 50 feet? Well, you might recognize that you have 50, 50, right triangle, right? This is a 45, 45, 90 triangle. So we can immediately see that the tangent here of theta is going to be 1. So we know that theta is pi over 4. Another way of thinking about it is that tan theta is equal to 50 over 50, which equals 1, and that implies that theta is pi over 4. Now, the equation needs to relate theta and x. And so we notice that the tangent of theta is equal to x over 50. Let's go ahead and differentiate this implicitly with respect to time. So d dt of tan theta equals d dt of x over 50. The derivative of tan theta is secant squared theta, and then we need a d theta dt here, implicit differentiation. And then on the right-hand side, we have 1 over 50 dx dt. Now dx dt is the quantity we're looking for. D theta dt is right here. This is d theta dt. I should have labeled it earlier. But now we also need the secant squared theta. Well, at the moment we're talking about, theta is pi over 4. So secant squared pi over 4 is the same as secant pi over 4 quantity squared, which is equal to root 2 squared, or 2. So now we're ready to plug in what we know. We have 2 times 20 pi is equal to 1 over 50 dx dt. That'll give us dx dt. When we multiply both sides by 50, we should get 2,000 pi feet per minute, since x is measured in feet. Pause the video, do number 14. Number 15, water is pouring into a conical tank at a rate of 2 pi cubic meters per minute. The tank is 6 meters high and has a radius of 3 meters at the top. How fast is the water level rising when the water is 2 meters deep? So here's our conical tank. And inside we have a cone of water like this. We know that the tank is 6 meters high and has a radius at the top of 3 meters. And the known rate is given in the very first sentence. Water is pouring into a conical tank at a rate of 2 pi meters cubed per minute. That's going to be a rate of change in volume with respect to time. So we have 2 pi cubic meters per minute as our known rate. For our unknown rate, they want us to find how fast the water level is rising. That's going to be a rate of change in the height of the water with respect to time when h, the height, is 2 meters, when the water is 2 meters deep. So we need an equation that's going to give us a relationship between volume and height. Well, the volume of a cone is 1/3 pi r squared h. And you'll notice that we have two variables there, an r and an h, but really we only care about the h. So we're going to take a close look at our two cones, right? The black cone and the blue cone, and use their similarity to eliminate one of our variables. In other words, we're going to notice that we have this green triangle that's changing in size. It's a right triangle. This green right triangle is changing in size as the water rises. H gets longer, R gets longer. We also have this fixed black triangle here, which has a height of 6 meters and a base, if you will, of 3 meters. And so what we have here are similar triangles. And whenever we have similar triangles, the corresponding sides are proportional. What that means is, if we take the ratio of R and H, that has to equal the ratio of 3 and 6. Simplifying that down, we get that R is equal to 1/2 H. And what we're going to do is we're going to take this quantity and plug it in there for R, so we have a function of one variable only. So this becomes V equals 1/3 pi 1/2 H squared times H. If we simplify this down, that becomes V equals, when we square a half, we get a fourth. We multiply that by the 1/3, we get 1/12 pi, and then we have H squared times an H, which gives us H to the third. This is the equation now that we're going to differentiate implicitly with respect to t. So we're going to take the derivative with respect to t of both sides. which looks like this: dv dt equals 1/4 pi h squared dh dt. Now we plug in what we know. We have dv dt is 2 pi. We have h is 2. Simplifying this down and isolating dh dt, we get 2. And this is a rate of change in the height, which is measured in meters, and the time is per minute. So there is our final result. Go ahead and do number 16.